Okay. Cool. So if you can see this little data, you can't really see that, but
Bring it down a little. Bring that down a little bit.
That's a good idea. Can it do that? All right. Well, it's right there in the data tab after you enable it. So let me show you how to enable it real quick. You gotta go to File, Options, the add-ins, and then mine shows that it's active. It's called the Analysis Tool Pack. You could just leave this on Excel add-ins and say Go, and then you have these that they're already included with Excel. I don't think you have to download anything. There's one that is VBA enabled or whatever, and then just the regular one. I just have the regular one. But then if you have a data set, you just click on this and you pick what you want. So there's several stats that it'll run, t-test. It'll do simple, basic regression stuff. Fourier analysis, does quite a few things. Yeah, Nova.
So I gotta figure out which one of them was
that you would
considered factorial.
I'm not sure.
And SPS might.
Yeah, I'm not totally sure, but it's a nice little tool pack or add-in.
I had one thing with the data for the lab. A little different.
For what?
For the lab.
Right.
My two graphs are almost identical.
Well, and that's
So I kind of wrote an answer for the conclusion going, I'm assuming that I can do either or and it does exactly the same stress to my back.
That's a logical conclusion from that. So
and that if I have a knee point, maybe I can make a stronger conclusion of which one's better.
Yeah. So Dr. Fogelman had mentioned that when I talked to him. I just want to make sure I can see the mic. Okay, the volume is just double checking.
But the one when I crouched down and squatted, it was still a little better.
So when I talked with Dr. Fogelman about this, he said that the reason he has students lift that high is because if it was a lower lift, you couldn't really see the difference. And apparently, even at that height, you still can't see much of a difference between the two lifts. So that would be a conclusion I would draw, given your data is it doesn't make a big difference in terms of the moments, the torques on your back.
I wasn't able to put it in PDF format. Is Word good?
That's fine.
Okay.
I didn't even know
That's
it
fine.
was supposed to be in PDF until she mentioned it.
I mean, I guess I didn't on Canvas. Did it say that, or on the actual?
It's on the actual paper.
Okay, so that's how Dr. Fogelman prefers it. As long as I can read it and it's like formatted and there's not something crazy going on, then I don't care.
I'm like, oh, son.
Yeah, don't worry about that. I've got to duplicate, otherwise you're gonna get the little presenter view again. Hold on a minute. Maybe. Please. Okay. Oh no, it's still doing the presenter view. I know I can turn that off too, but I swear. Okay. All right. So I posted a lecture on this last half of the biomechanics lecture, and we're not going to go through everything in detail, but I'm going to refer to some things as we work through an example problem. uh, basically identical to what you're required to do for your exam, but with some different numbers. So through the whole process. And so one thing, let's point out again before we jump to, I'm going to jump into Excel, but well, so I'm going to show you a secret. I'm sure you would have figured it out anyway.
That says to turn it in on even a file.
Right. So I would like it to be by hand,
Okay.
but I'll show you how you can check your work in Excel, and all you have to do is copy and paste a couple numbers, and then you can have all the answers. So you will have all the answers, but I do want to see the handwritten work. That's why I want the handwritten work, is because it's already all set up for you to just, I don't want to test your ability to copy and paste the numbers and then write the correct numbers. So, all right. So let's say, so we have that forearm there. I'm going to do like a dumbbell, and forgive my art. That marker isn't great. All right, so we've got someone lifting a dumbbell. We're just, for this portion of the exam, we're only worried about the forearm and the hand. We're not going to do anything else. So I took my ergonomics class in grad school. We only did it by hand. We didn't have a cool Vicon system like Dr. Fogelman, and we did it for the whole body, and that was painful. But anyway, I think the way Dr. Fogelman does it is better. So let's pretend you're just holding this dumbbell still. And one thing that we talked about is due to gravity, there's a force pulling down on the dumbbell, right? If you let go, it's just gonna fall. So we have a force here. I'm gonna. Where's the trash can? See, dang it. That's why I didn't play competitive basketball. I still like basketball, but so I'm gonna put that dot there. And in addition, it's not like our forearm and hand is made of air. There's a weight to that as well. So when you lift the dumbbell, you also have to lift your forearm, right? That's why, like if you do a squat, you're lifting your whole body plus what's on the bar, right? So, I'm gonna put it out here just to represent the forces due to gravity on your forearm and hand. And here we have forces due to the dumbbell. I'm just going to put D for that. So we have these two forces working against us if we're doing bicep curls. Hey, Amber. So if you're doing a bicep curl, you have to lift the dumbbell plus your forearm, right? So your bicep is lifting both of them. Due to gravity and the weight, the mass of the dumbbell and your forearm and hand, there is a force pulling down. So if you're holding that dumbbell still, that means your bicep is applying a force that is canceling out these, basically. So remember, if you took the sum, if it's holding still, if it's static, and you took the sum of all the forces, it'll be 0. Okay, so I don't know where to draw this, but let's say this is the force of your bicep. And if this was 5 and this was 5, then this would be, actually these would be -5 and -5 because they're going down. And that would be 10. So if you add all those together, what is it? 0. Good. And again, I'm just making up those numbers. Okay, so that's what this is saying. is the weight of the load, or the force of the load due to gravity, and the force of your forearm and hand due to gravity, plus the RE here is a reactive. It's a reactive force that's external. That's what that's referring to. But basically, in this case, it's your bicep. So this would be your bicep. So here it gives these two numbers in this example. It's -49 and -15.8. So your bicep must be doing 64.8 newtons in the positive direction, whereas these are both doing that in the negative. Okay. So that is a linear example where we're just talking about up and down. We're not talking about actually what your bicep does, which is curl. So it's not just up and down. There are other forces at play. And so that's what we're looking at when we look at moments, is we have distance involved, and we're going to talk about angles. So, but before we get into that, I want to just cover some basic ideas. I'm going to use mine because I think they write better. So let's say we have a teeter-totter. And let's say, well, I mean, I'm thinking of my kids, but let's say one of my kids is on it right here. Is it gonna do anything? What if they move to right here? A little bit, good. So to counterbalance that, you probably wouldn't have to put very much weight on the other side. What if they moved out here? You'll need a larger one, good, to counterbalance that. So when we talk about distances, we're talking about the distance from that fulcrum. Okay, so it could be here or here, and the farther you get away from that fulcrum, the more force is exerted. So if you think about your back, your lower back as a fulcrum point, or your hip joint, if I lean this much out, there's not a lot of forces on my back. But if I lean this far out, then, I mean, with no weight, it's not that uncomfortable. But you can imagine if I have a squat rack, a bar in the squat rack, and my back is out this way, which is bad form, but it's gonna hurt a little bit maybe. If I lean this much with the squat bar, I'm probably gonna do something to my back. Okay, so the forces start to increase, not exponentially, but it's not linear. It's more than linear. Okay, so I want you to get that concept. As you move away from the fulcrum, the forces, the torques exerted just get bigger and bigger, and they increase pretty quickly. So that's what's happening with moments. We're also going to throw in angles because the angle matters. But that's the idea with that. So in this case, with this example, we won't do the math just yet for this kind of an example, but it's looking at the distance of the load, and it gives little tiny numbers that you can't really see. But from here to here, it's just assuming, well, I'll talk about what we're going to assume when we do this in your problem. It says 35.5 centimeters. So that's the distance from the center of the elbow to this load, the dumbbell. And there's did anybody watch that lecture, by the way? I won't be offended if you haven't, but I just wanted. Yeah, the one that I did like on Sunday, or Saturday night. So it hasn't.
I haven't.
No worries. I sent a thing through, like a message through Canvas, but no worries. If you want some background on some of the things, I'll mention some of the things that I find curious and maybe morbidly humorous about some of these measurements. Again,
It's gonna turn morbid.
well, you'll find out. But anyway, so the center of mass from the middle of the elbow to if you look at the hand and the forearm together, I mean, they're saying it's right here. So 17.2 centimeters. So that's the distance then that we would use for the forearm and hand, and the distance we would use for the dumbbell is this full length. So torque is, I refer to it as torque. I guess technically it's moments, but they're basically the same thing. It's a force, but it's a rotational force. And so we take the distance times the force, or the distance times the weight. The weight here is mass times gravity. Yeah.
I'm gonna be a little shit.
No worries.
On the hand part, why didn't they go all the way to the end of the knuckle instead of like in the middle of the hand?
So that's one of the assumptions that we're gonna make, is to avoid getting too complicated. So I guess to mention that morbid part. So someone has figured out that, so this is height, okay? H is height. Someone has figured out that on average, again, there are people with like gorilla arms or like T-Rex arms, but generally the length of your upper arm is about 18.6% of your total height. And your forearm is about 14.6% of your total height. And your hand length, which is longer than I thought, but 10.8% of your total height. How do you think they figured that out?
You do like a string wrap. After you do you wrap your string around your neck sometimes it plays your weight.
Well,
It's only supposed to be one.
I've heard.
But yeah, if you're testing your pants, if you want to go shopping and you don't want to wait in line, you just grab pants and put it around your neck, and then it's exactly your waist.
I've heard that as well. I haven't really tested it out, but does it work?
It works perfect. That's
Really?
how I shop for jeans.
So I'll have to try that out. So with this one, it doesn't necessarily involve dead bodies, but you could just measure live people, their height, and then measure this, and then measure this on 100 or 1,000 people, and take the average to get these numbers.
But you say the morbid part was
The morbid part, I'm saying that they probably did measure on dead bodies because of this next part, because they had those dead bodies. They had to have those dead bodies for this part. So, how do you think you figure out where the center of mass is for a forearm?
By splitting it out there,
By chopping it off and then putting it on a fulcrum, balancing this dead person's forearm on. Okay, I'm serious. I'm serious. So you wouldn't want to start that way. First, you would do the whole arm, balance that, and then people donate their bodies for science and stuff. That's if you go to med school, that's if you donate your body to science, then who knows what will be done to you. But anyway, so anyway, that's the interestingly morbid and somewhat, I don't know, humorous part, I guess, about this. But anyway, so those people who cut bodies up and did all this testing found out that if you take just the forearm and the hand, if you weigh it, so this is the weight. So I mean, how do you find the weight of just the forearm and the hand without chopping it off, right? So they took someone's forearm and hand, and they weighed, I don't know, 1,000 of these, and they found out that it's generally 2.2% of your entire mass. So if I'm 100 pounds, which I'm nowhere near, but then my forearm and hand would be 2.2 pounds. Okay. And then that's how they found out the center of mass as well. So this is a percent of the length. So if you're starting from, well, proximal means closer to the core, right? And distal means distant, farther away. So what this means is if you start at the elbow and you go 68% of the way down that length, somewhere in there, that's where that's where your forearm, if it was chopped off, would balance nicely on the fulcrum. and if you look at the distal, that just means from the end of your fingertip, if you came 31% of that length down. So, I mean, this should equal 1, right? If you add these up 100%.
1,000 people. 1,000 forearms.
I don't know how many they decided was sufficient, but
Do that thing where you like water and like calculate like water.
is display. So you could find the volume. There are probably ways where you could estimate it, but there's only one way to.
Scan it with like a laser.
There's only one way to know for sure. And these data were produced a long time ago, so they didn't have the fancy lasers and stuff that you're talking about. I'm pretty sure. I mean, my ergonomics professor, who would have known, that's what he said. That's what he said. So anyway, all right. So the whole reason for, I mean, so these numbers allow us to estimate the mass of the forearm and hand just with the mass of the person, and the length of their forearm and hand with just their height. So all we need to know is their height and their weight, and we can estimate that stuff. And the center of mass is important because we're talking about this fulcrum. So if this is your elbow, how far out is that center of mass where force is moving down from your forearm? So that's why we have to figure that stuff out. So here's the secret that you guys are in on because you're here, and anyone else who might be listening who didn't make it to class. Your portion of the exam that I changed to October 9th. So let's do October 9th. What is going on? Okay. Looks just like this, right? But this is somebody else. This is right. I don't know where Dr. Fogelman got these names, but anyway, you have a mass and a height for your subject. You have a mass of the dumbbell or load. I'm just going to assume a dumbbell. And this person, this is a, well, I don't know. This is a,
What?
this isn't one of those fancy screens, is it? No.
No.
I don't know why that happened.
That's not
Ghosts. We've been talking about too many dead people. They're not happy. All right, so so we also have the location in space, at least in a two-dimensional plane. Next. Wow. Okay.
I'm not okay with this anymore. No, I am not.
Yeah. What is going on here?
Some holy water, you'll be good.
And some salt.
Yes, garlic. Sure good. Garlic doesn't work.
Let's see if changing the layout helps.
Why don't you watch Supernatural? It doesn't work.
No, it doesn't, unfortunately.
That's why you need a shotgun that has rock salt in it.
Maybe we go
Nice.
and you shoot them in the face with salt. I love Supernatural.
Or we just need the cold.
Why haven't they come up with Hulu?
Okay, we'll see if this helps it to not be crazy. All right, so we have our location, the location of the wrist and the elbow in space in 2 dimensions. And your assignment is to calculate the reactive force, which, remember, it doesn't include the distance or the angle or anything. It's just if this was going up and down, like that first thing we did, just the force. And we're going to walk through these and do it by hand, which is what I want you to do. And the reactive moment at the elbow. Okay, so basically, what sort of forces are being applied at that fulcrum to bell still? Note your sign convention. So the forces that are going down generally are negative. So your forces will be that you report will be positive. So you're reporting the forces that are holding it up. Okay. What your bicep is doing. Go ahead and diagram it. I mean, you could do something kind of like what I'm doing. Hey, Ash. Kind of like what I'm doing. It could be a stick figure. Just do the upper arm to the elbow to the hand. Like, it doesn't have to be fancy. Just diagram it somehow. I want something visual. It should help you also to kind of visualize. And make sure you include units. I had a professor who said a number just by itself means nothing to him. It has to have units. So somehow indicate what it is. And we'll see if it still does that thing. But anyway, anyway. Okay, so here's the secret. I mean, secret. You can use this to check your work, but again, I want what you turn in to be by hand. So we're talking about the problem portion of the exam 1, which is now due October 9th. I pushed it back because I wanted to do this in person and not a recorded lecture. Sorry, should have had this ready. Okay, so you can open up your spreadsheet from the assignment that you had and just copy and paste these into here.
So that's the same as lab assignment?
Mm-hmm.
Okay.
Yep, the lab assignment. So this is a way I would like you to use this to understand what's going on and to check your work, but I want your work by hand. And so I'm just going to paste those numbers right in there. And I need to update the height and weight. So 72.6 and 177.8. Wait, that's the wrong one. 177.8 and 72.6. And you can see when I hit enter here, the numbers below on the left side are going to update. So see some stuff updated. So it does all the math for you. Oh, also the load, which in this case, I think it was 35 kilograms. You can see everything is updated, and you have the reactive moment and the reactive force. So these are the two that you would be interested in. Let's see if I can zoom in there. So those are the answers. You can just enter your stuff in and you have the answers, but I want to see it. You work out the problem by hand. So that's what we're going to do right now. But this is just a way to kind of check yourself and make sure that you're on the right track. And actually, to be honest, this number would be better. Rather than Newton centimeter, do Newton meter. Okay, so to do that, we start with, I should have written our heights. Oh, and it's doing it again. Let's see here. Okay. What did I say for heights and stuff? I'm gonna turn the light on. So it's gonna be kind of weird. We're gonna have the light on and the projector on, and I'm doing stuff on the board, but yeah, I think it'll work. Okay, so what did I say? 72.6, and our height was 177 point. Dang it! Does anyone remember? Kilograms.
I guess it doesn't really matter.
Yeah, it would just be nice to be able to check ourselves on the spreadsheet. 0.8 and 35 kilos for the. Let me just leave that up and then write it. So I'm gonna put trying to think of, yeah, I'll put D for the dumbbell. I'm gonna say it's a dumbbell, but oh no, it's 35 kilograms even. And then we have our XY for the wrist and XY for elbow. I didn't give myself enough room, I don't think. Okay. Is that negative 28? And 128. So in my grad class, we didn't have the location, XY coordinates for the location of the joint in space. So we had to use trigonometry to figure that out, starting at the ankles, working through every joint all the way up, down until, yeah. That's why it was so time consuming and painful. All right. So first, let's start with the easy stuff. The forces. And for the forces, you don't need to know exactly where it is. You don't, where the center of mass is for the forearm and hand, or where the dumbbell is exactly, because it's just a force. It's just, we're assuming if this was just something that goes up and down. When we get to the moments, then we do need to know that stuff. So I'm going to skip this slide. We'll come back to it. Because again, we don't really need it yet. So we're not using these numbers, but we're going to do the same thing. So quick review. The sum of all the forces should equal what? If it's static. If it's static, then it's 0. Right. And does anyone remember the little equation? So it's a negative weight of the forearm and hand minus the weight of our dumbbell minus, I guess that's really plus, the reactive force that's external, which is, so this is the bicep. What is the bicep doing to hold it all up? And all of that should equal 0. So what could we do to this equation to solve for the bicep, what it's doing? Just subtract this over here, right? So the force that we're interested in, I'm just going to say it's the force of the bicep. But again, the technical term is the reactive force, is the weight due to gravity of the forearm plus hand plus the weight due to gravity of the dumbbell. And the equations that we have on here say W, but right. So what's the difference between mass and weight? No, but mass is related to, it's like your overall makeup. So if you were on the moon, your mass would be the same. But because the gravity is less on the moon, your weight would be less. So that's the, I guess it's not easy to get to the moon, but if you want to weigh a lot less, then go to the moon. So weight, when we say a weight, we're referring to a force. And force equals what? Acceleration, good. So we need to know the mass of the forearm and hand without chopping it off. And we need to know the mass of the dumbbell. So we have, well, we have this one. We're going to have to figure out this one with those, the numbers that are right there. Also, what is acceleration due to gravity? we'll just go with 9.8 meters per second squared. So for each of these, we're going to have to break that out. We can do this one right now. So our dumbbell is 35 kilograms times 9.8 meters per second squared. And that's the units that we get at the end of that is what a Newton is. That's what a Newton represents. And how much is that? Go well. Or we could look up the answers. But it's, I think I remember what it is because I was reviewing. So 343 newtons. Cool. So sorry about that, but so for this one, it's a little bit harder. We got to do some more work, but not a lot. For the forearm and hand, the segment weight compared to the total body weight is this right here. So your forearm and hand are about 2.2% of your total body weight. So what we need to do is do 0.022 times this Wright's, I'm assuming that's the last name, but Wright's total body mass. So that's 72.6 kilograms. And what does that come out to be? I think it's like 1.6 kilograms, if I remember. And then you don't have to do that math, but just know that that's what we did. I know you can plug numbers into a calculator. And then we multiply that by 9.8. So this is the mass of forearm and hand. It's what the bicep is having to hold up. So you have to hold up that plus the dumbbell. And that is 15.6 newtons. Again, I'm not doing that in my head. I just remember from reviewing this problem. Okay, so it's kind of hard to see because of the screen, but these are our two forces. So we just need to add those together. We get 3, what is that? 358.6 newtons. So that is the first answer. And
Combine the 3,
Oh.
3, 15.
yes, 343 plus 15.6. And I am confused. So this was doing the whole presenter view again. You got to make sure it doesn't do that. Maybe there is like a ghost controlling my computer. I don't know. So, okay, so I'm just checking myself here, and I highlighted it on the other one, I think, but we're right. We got it. So 358.6 is the reactive force. Now we need to do the reactive moment. A little bit more involved, but still doable. So now we do care about this. We care about the distance of the center of mass from that fulcrum. I don't know why my computer is doing this. All right. Apparently, I think I pissed the ghost off or something. So, where are we? We need to go back one. Yes. Oh no, this is the right. It's just exactly in the same spot. This is the right, correct slide. So can I erase the work that we did before? Is everyone got it? All right. Now, we do care about where that center of mass is and the length of the forearm. Dr. Fogelman calls this L1. I'm going to call it LF plus H. We also need to know the length, the distance from the elbow, the fulcrum, to the center. So this is the entire, like the tip to the tip of your finger from from your elbow to the tip of your finger. And we're assuming that's where the dumbbell is, although, in real life, it wouldn't, Brittany brought up, in real life, it wouldn't be at the tip of your finger. It'd be a little bit closer, but we're not going to get that technical. And then lambda 1 is what I'm going to call the length of the center of mass for the forearm and hand. So just so you can translate between the notes and what I'm doing right now. Center of mass, COM. We could, or if it's easier, we could just say length to the dumbbell for that one. All right. So length, forearm and hand means the length of the elbow all the way to the tip of your finger. And length of the center of mass is the length from, it's this one. Why don't I just label this? Let's say that's the center of your elbow. This is L, and this to that point is L, F, and H, the full length. And that's what he refers to as L1. What he refers to as lambda 1, we're calling L. Okay, so for the full length, it's really small. There's maybe we'll go back to the slide where it's larger here. We want to know, so this is the hand and this is the forearm. We didn't know the length from here to here. So how could we do that? Yes, we can kind of combine it to save a step. So we take our height, H, and then multiply it by these numbers. So we have height 177.1. I do a funky 7 times, and then we're just going to add up these two numbers. So 0.146 plus 0.108. And that gives us 0.254. So we multiply these two together, and I don't remember what that number is. It's 25% of that, so it's got to be like 40, 45.
Yeah, like almost 44.9.
Oh, okay, cool. My memory might not be fading so much. Okay, so let's label this in green. How about that? So this is, I'm going to erase that and that. 44.9 centimeters. Now that we have that, we can figure out this one. So now we have to go back to that other slide. Or we could stay right here. Although that is in the way. So this is the upper arm. We don't need it. This is the forearm and hand, which is what we want. It tells us exactly where they're measuring. And here we will need this number for the mass. Actually, although we've already computed that, right? So, and I think I erased it. Dang it. Yeah, let's write those down. So what is the mass of the forearm and hand? I'm going to say dumbbell weight of the forearm and hand. Sorry?
15.6.
Actually, I guess this is a mass right here. But yeah, I think that's all we need there. I think. If we'll figure it out if we need more. Okay. So do you remember what it was in? I think it was like 1.6 kilograms, right? The mass. So the mass of the forearm and hand was 1.6 kilograms. Right, because the 9.8 times that gave us that. Okay. All right, so that's the mass, but now what we're interested in is this distance here. So if you travel 68% of the length from your elbow to your finger, stop at 68%. That's where the center of mass will be. That's where if you chop your forearm off, you could balance it on a, yeah. All right. So all we need to do then is take this number and multiply it by the 0.682. So we're going to take this number. This is the full length. And what that is telling us is 68% of the way down is where the center of mass is for the full thing. So we do 0.682 times 44.9 centimeters. And that should give us something like 30 centimeters. If someone could do the exact. So we are going to be one lecture behind, and I'll figure out what to do. We might. We'll either breeze through one or cut it completely. We'll see. We'll see. I mean, we'll still have the same number of classes. It's just we won't cover some material, but that's okay. I'd rather you know how to do this. So this is like a core part of ergonomics. What is it exactly? Did anybody know what is it? That's groupthink. This one. 30.5. We'll go with it, and then we'll check to be sure. Okay, so we have these two lengths. This one is 30.5 centimeters. So now we have the lengths, which is, if you think of that other equation I had, it was d, the distance. All these different, the variables keep changing. Anyway, so, but basically it's the distance from the fulcrum. If we multiply that by the forces, then we'll get the moments. Now, we could do that if this wasn't at an angle, then we could just do it straight up like this right here. Unfortunately, we're at an angle, but if this was not at an angle, just straight, parallel with the ground, then this is what we'd have. We could do this 30.5 centimeters times, so this is the center of mass of the form, times 15.6. We will actually have to use these numbers, but we have to do more as well. So the weight, or it's the moment. Well, see, it calls it D, although we call it L. But all right, so let's do the dumbbell first. So the dumbbell weight was, what was that one? I didn't write that one down either, huh? I think that was everything. Oh, yeah, you're right. You're right. The weight, 343 newtons. So what we'd do is we'd have 343 newtons times, now that's the weight. I'm doing this a little bit out of order. The distance, so it's 44.9 centimeters away from the fulcrum. This is a negative. And then for the forearm, itself, we have 15.6 newtons times 30.5 centimeters. So that, again, if there was not an angle involved, that would be our answer. But there is, so we got to keep going. Does that make sense? This is the one time where like having swivel or something on the board would be helpful. I mean, one example of where that would be helpful, but you've got your notes, so so that's good. Okay, so that's how we would do it if we're just straight, but we're not. We're something like this. You know, this is we're halfway through the curl. Well, no, not even halfway. Now for the trigonometry. Fun. All right.
So what is, because it's the sum of moments, so what is ME out of that?
So it's we'd have the moment for the, I'm going to abbreviate, the moment for the dumbbell minus the moment for the forearm and hand plus the moment for the bicep, or, you know, whatever you want to call it, equals 0. So we'd move that over, and then basically these two. Right. So if you put those two together, it'll give you the moment of the bicep. So that's, yeah, I didn't complete it. I just was putting that up there. So again, if there was no angle, if it was 90 degrees, I guess, actually, I mean, I guess that's an angle, but if it was parallel with the floor, then that's all we'd have to do. But it's not. Can I erase the red up here? All right, so first we've got to find our angle. So this is the free body diagram that the exam question talks about. You know, do something like this. You could draw the actual arm and stuff if you want, but have this, and then at least this. So we have X and Y for the elbow, which was negative 28.054 and 128.629. And the X and Y for the wrist, negative 7.987 and 118.664. So we have their locations in space. And one thing that, again, so the trigonometry, so we're going to imagine lines right here that create a right angle so that we can use our fancy trig functions. And basically what this does for us is it gives us the angle. We're going to need the angle because we have to take the cosine of the angle at the end. And that's actually the only thing that's missing from these. That's why I wrote them, and I'm leaving them for now. So there's one more term that we've got to include in these, and that's the cosine of whatever the angle happens to be, you know, this inside angle. So, but I mean, so you've all done a bicep curl. At what angle is it hardest? So when you, I mean, if you're fresh, let's say you're not like exhausted because you've done 100 reps, but you know, your first rep, so it's in the middle. It's in the middle. So if you've got the dumbbell up here, like finishing this is not difficult because of the angle that is being created. There's not a lot of pull downward. Then the same with out here. I mean, when you get tired, like starting and finishing does get hard. But really where your bicep is exerting the most force is when it's making a 90-degree angle. So I just want to point out that the angle does matter in terms of the forces being applied by your bicep and on your elbow. So, all right, so we've got to use this. The angle, theta, equals the inverse tangent of rise over run, basically. So assume that the higher point is number 2 and the lower point is number 1. So our elbow is number 2 and the wrist is number 1. So in our case, we need to do that math. We get, so theta, our angle, equals tangent, inverse tangent of, I'm not going to write the decimals out just for time, but we've got x and then y, right? So we have 128 minus 118. Again, I'm not writing the decimals, but you should include that. And then we've got negative 28 minus a negative 7. And that equals, don't do the math. You will have to do it, but just because of time, I'm going to look it up. Again, that's the beauty of doing this little shortcut. If I can figure out where that is on here. Oh, that's theta. So I don't know what those numbers would be, but actually we can figure that out here real quick. Apparently it's negative 0.49. Does that seem to make sense? That's about 10, and that is about negative 20. Yeah, that's about right. So negative 0.49. So if it was 10 and 20 exactly, it would be negative 0.5. Negative 1 over 2. So we did it right. So, well, so it's not. So this is sorry. Good question. I should clarify. So that negative 0.49 is this part in the parentheses. So you do inverse tangent of negative 0.49. And when you do that, then you get this number here. As your angle, negative 26.4. Just want to double check. Yes. And that's in degrees. It's important to convert that to radians. So most calculators will do that, or you could do it in Excel. So use this formula right here. I'll write it out. Equals cosine radians, and then whatever the angle is in degrees. I'll leave that one up there. B32. Yeah. Sorry. Yeah, I left the cursor right there. 0.89. So if we do that, then we get 0.89 radians. Okay. So we've made it through this part. So here we get an angle in degrees. And that's okay. You know, I know how to stop the presenter view. Where is it? Here. Stop. Okay. It's not possessed. It's just user error. Okay. All right. So now we're at the final piece. Can I erase the red? So we did this one already. We found these, this here and this here, added them together. We got our answer, 358.6. That one's done. We don't have to worry about it. It's this one that we've got to do. So we have the moments of, I'm not sure what he's referring to with L, but the dumbbell. Yeah, this is the dumbbell, and this is the forearm and hand. Adding those two together will give us this, so we just subtract that over to that part of the equation. So now what we do is, because we had angles involved, we couldn't do this, but we can just add to this. So just wanted to put those there to remember. So now we have negative cosine of our angle. I guess in Excel, it has to do it in degrees, or maybe he converts it to radians for his program. But if you're just doing it on a calculator, I think just doing the degrees is... let's try it on a calculator. I haven't tried it on a calculator. I've only in Excel. So what was our angle? Negative 26.4 times, let's do it in the correct order here. 44.9 centimeters times, let's turn this off now for a minute. Is it possible to just hide? Maybe not. Well, yeah, maybe it is possessed. Okay, it's just funny to see the remnant. Times 343 newtons minus cosine, again, of negative 26.4 degrees times, now are we pulling from the other one, 30.5 centimeters times 15.6 newtons. So I would like to try this on a calculator. If anyone gets it before me, let me know. I'm not sure I can even add a negative sign. What is this? I mean, on your phone. Well, I'm using this app, and oh wait, that's why I brought this. I don't know why. And I even slept good last night, so I have no excuse. Okay. So you said you're calculating. Oh, hey. Cosine negative 26.4 times the number is looking about right. So this one I get 13794.6. Did anyone else get that?
That was correct on.
So I did this first, and then I just multiplied these two.
Question, is that a negative in front of there?
It is. Yep. So now let's try the same here. That times 5 times 15.6. And I get 42.6.2, and then adding the two together, I get 14220.8. And the thing is, this is newtons centimeters. I would prefer Newton meter. So you just move this 3 over, so it would be 14.2 newtons meters. And let's pull up the all-knowing Excel spreadsheet to see if that's right. It's close. I remember the number is something like that, but hopefully the projector will come back on. I think, oops. No, meters to centimeters is not 1,000, it's 100. It's a difference of 100. So yeah, 142.2. And Excel, this is showing I see what so forget the radians thing. That was simply calculating what cosine of negative 264 is. So when you do that, it's anyway. So if that will come on. Oh wait, it's on the wrong thing. Come on, please. So okay, so here's, if you enter in Excel to check your own work, I mean this is the line you care about for the angles. So this is the angle that you'll calculate. When you take the cosine of that, you'll get 0.8956. So I mean this is the equation that Dr. Fogelman used to calculate that in Excel, but it's really just taking a cosine of that angle. And then, so all of our numbers are right, but it's slightly different from his. Yeah, that's a possibility. I mean, it's close enough that I think it's just some rounding. Oh, see, and he has 15.7, so he rounded a little bit different than we did there. I'm just curious for funsies if we change this to 15.6. Well, it's closer, but anyway, there's probably a little bit of rounding involved. If it's just a little bit of rounding, I'm not going to worry about that too much. And that's kind of painful to look at. But any questions? I think we're done. Like I said, we will we'll figure out what to do because we're a little bit behind. But so this would be the other answer. A little bit more involved than that first answer to do the moment. But any questions? So October 9th is the due date for that from your exam.
Same time, same place.
Yes.
Yeah. Can I erase? You know what? I need to turn off live stream. So as I've mentioned, I'm fine with